Welcome to the Sleepy Cosmos Stories channel. I'm truly happy you're here. Before we begin, I'm genuinely curious, where in the world are you watching tonight? From a quiet bedroom? From a comfortable chair? Or perhaps stretched out in bed after a long day, simply wanting to rest? Wherever you are, I hope you're comfortable, safe, and in a moment where you can let your thoughts gently drift away. If you enjoy these calming cosmic journeys and would like to hear more, liking the video and subscribing helps this small channel continue on its path. And to those who are already subscribed, I offer my sincere thanks. Your support means far more than you might realize. Now, I'll try not to make tonight's topic so exciting that it keeps you completely awake, but if you do happen to stay awake, at least you'll have learned a billion-year story of the universe, from beginning to end, from heat to cold, from light to darkness, and perhaps back to light again. A small price for a sleepless night. So, shall we begin? But not just from the beginning, from the absolute beginning, before everything, from the moment when time, space, matter, and energy did not yet exist. From nothing. Close your eyes. Imagine there is nothing. Not even darkness, because darkness is the absence of light, and here, even the concept of light does not exist. Not even silence, because silence is the absence of sound, and here, even the concept of sound does not exist. Not even emptiness, because emptiness requires space, and here, space itself does not exist. There is no time, no past, no future, just nothing. Or perhaps everything, but compressed into an infinitely small point, a singularity. We don't know, because our physics breaks down there. General relativity says infinite density, infinite temperature. Quantum mechanics says uncertainty, fluctuation. The two do not merge, and so we do not know what truly happened. But we do know this: a moment came, and in that moment, everything changed. The Big Bang. Not an explosion, an expansion, sudden, violent, and irreversible. Time began, space unfolded, energy burst forth, and the universe was born. The first second, from quantum foam to matter. T equals 0, Planck time, 10 to the minus 43 seconds. The smallest meaningful unit of time. Before this, there is not even a before. Time is uncertain, ruled by quantum fluctuations. Space-time is like foam, bubbles forming, popping, and reforming. But then something changes. Inflation begins. T equals 10 to the minus 36 seconds. The universe expands exponentially. In less than a trillionth of a second, it grows from the size of an atom to the size of a galaxy, perhaps even larger. Why? We don't know for certain, but one theory points to the inflaton field, a high-energy quantum field. As the universe expands, this field supplies energy. The universe grows using its own energy. T equals 10 to the minus 32 seconds. Inflation ends. Energy turns into matter. E equals mc squared. Einstein's most famous equation. Energy and matter can transform into one another. And in that moment, the first particles are born. Quarks, one of the most fundamental building blocks of matter, extremely small, extremely light, but extremely energetic. Gluons, the particles that hold quarks together, like cosmic glue. Electrons, light, negatively charged. Photons, the particles of light. Neutrinos, ghost-like particles that pass through almost everything. But there are still no atoms because it is far too hot, trillions of degrees. Everything is plasma, liquid energy. Particles constantly collide, combine, and separate. Chaos. But at the same time, creation.
The first microsecond, quark-gluon plasma. T equals 10 to the minus sixth seconds, 1 microsecond. The universe has cooled. By cooled, we still mean trillions of degrees, but cool enough that quarks are no longer free. The strong nuclear force comes into play. Quarks bind together in groups of 3. The first protons form, 2 up quarks and 1 down quark, positively charged. The first neutrons form, 2 down quarks and 1 up quark, electrically neutral. This is a monumental moment because protons and neutrons are the building blocks of atomic nuclei. Without them, there are no atoms. Without atoms, no molecules. Without molecules, no life. So, at this moment, just 1 microsecond in, the foundations of life are being laid. But there are still no atoms. It is still far too hot. Electrons cannot bind to nuclei. They are constantly knocked away. The universe remains plasma. Yet, it is cooling, slowly, with every passing second a little cooler. The first second, the freedom of neutrinos. T equals 1 second. The universe is now about the size of a basketball court. All right, that's an exaggeration, but after inflation, expansion feels slow. The temperature is around 10 billion degrees. Protons and neutrons are stable now. They no longer break apart. And something else happens. Neutrinos are set free. Neutrinos are ghost-like particles. They barely interact with matter. Every second, trillions of neutrinos pass through your body, and you don't feel a thing. Until the first second, neutrinos were interacting with other particles. The plasma was too dense. But now the universe has expanded enough. Neutrinos decouple. They spread into space forever. And those neutrinos are still out there, the cosmic neutrino background, one of the oldest remnants of the universe. If you had a neutrino detector and extraordinary luck, you might catch one, and that neutrino would be 13.8 billion years old, born in the very first second of the Big Bang. Silently traveling forever, the oldest wanderers of the universe. The first 3 minutes, the birth of the first atomic nuclei. Time equals 3 minutes. The universe has cooled enough. The temperature is about 1 billion degrees. Still extremely hot, but below a critical threshold. Nuclear fusion is now possible. Protons and neutrons begin to combine. The first helium nucleus forms. 2 protons, 2 neutrons. Helium-4. Deuterium forms. 1 proton, 1 neutron, heavy hydrogen. And a small amount of lithium, 3 protons, but very little. This process is called Big Bang nucleosynthesis, the formation of the first nuclei. But it lasts only about 17 minutes because the universe cools rapidly. As the temperature drops, fusion stops. In the end, the universe is made of 75% hydrogen, a single proton, 25% helium, tiny traces of lithium and beryllium, nothing else. No carbon, no oxygen, no iron, no gold. Only the lightest elements. But it is enough, because from these elements, stars will be born, and inside stars, heavier elements will be created. But that comes much later. For now, there is only hydrogen and helium. After 17 minutes, nucleosynthesis ends. Time equals 17 minutes. The universe is now too cold for fusion. Atomic nuclei have formed.
but there are still no atoms, because it is still too hot. Electrons cannot bind to nuclei. They constantly gain energy, constantly being knocked away. The universe is still plasma. Light cannot travel freely. Photons collide with free electrons, scattering endlessly, going nowhere. The universe is opaque. Not dark, because it is filled with light everywhere, but that light cannot go anywhere. It simply bounces around. Like a dense fog, everything is bright, yet nothing can be seen, because the light is lost. This state will last for 380,000 years. For now, the universe waits. To cool, to calm, to allow atoms to form. The first hours and days, silent expansion. Time equals 1 hour, 1 day, 1 year. The universe expands quietly. It cools but very slowly. No dramatic events anymore, just expansion, just cooling. Plasma everywhere, hot, bright, but invisible. Over time, the temperature drops to thousands of degrees, to hundreds of degrees, still no atoms. This period marks the beginning of the so-called cosmic dark ages, though it is not truly dark yet, just opaque. No stars, no galaxies, no planets, no structures at all. Only an endless cloud of hydrogen and helium, homogeneous, smooth, boring. But there are tiny fluctuations, quantum fluctuations, stretched during inflation. Those fluctuations will become crucial because matter will later clump there. Gravity will grow stronger, and the first stars will be born in those regions. But for now, we simply wait. For 380,000 years. Why 380,000 years? At that temperature, something changes. The universe cools to about 3,000 Kelvin, and at this temperature, electrons can finally bind to nuclei. We combination begins. Electrons and protons combine, and the first hydrogen atoms form. This is a monumental moment, because once atoms form, electrons are no longer free, they are bound, and photons no longer collide with free electrons, because there are no free electrons left. Light is released. The universe becomes transparent. For the first time, light is free. It can travel through space, across infinite distances. That light released at that moment still exists. The cosmic microwave background, the oldest light in the universe. That light gives us a photograph of the Big Bang, a snapshot of the universe at 380,000 years old. But that belongs to the next chapter. The legacy of the first 3 minutes, today's universe. The first 3 minutes were brief, but in those 3 minutes, everything was set in motion. Protons, neutrons, electrons, the building blocks of matter. Hydrogen and helium, the first elements. And from their ratios, astronomers understand the universe today. Because the amount of helium in the universe confirms the Big Bang theory. 25% helium, exactly as predicted. If the Big Bang had not happened, helium would not be this abundant. Stars alone cannot produce it enough. So those first 3 minutes are the universe's fingerprint, its evidence, its birth certificate. And now, 13.8 billion years later, those helium atoms still exist. perhaps in your body, perhaps in the air you were breathing. The legacy of the first 3 minutes is everywhere. Take a breath. Deep. Slow. In this first part of the night, you traveled to the absolute beginning. From nothingness, from singularity, to the Big Bang. In the first instant, quarks were born. In the first microsecond, protons were formed. In the first second, neutrinos were set free. In the first 3 minutes, helium was created. And for 380,000 years, the universe waited quietly, cooling, expanding, waiting for atoms to form. In the next chapter, we will witness that great moment, the release of light, the transparency of the universe, and then the Dark Ages. Starless, silent, yet full of anticipation. And then the birth of the first light, the first stars, the universe shining once more. But for now, just rest. Your eyes may feel heavy. They may close. Let your thoughts slow down. Let your body relax. Because the universe is still very young. Its first 3 minutes have passed, but ahead lie billions of years. And tonight, you will witness those billions of years together with it. Gently, peacefully, as you sleep.
In the first chapter, we witnessed the Big Bang, the first second, the first 3 minutes, the birth of matter, the creation of helium and hydrogen. But now, 380,000 years have passed. The universe has cooled, atoms have formed, and now a great transformation is about to occur. Light will be set free. The universe will become transparent. But then, the Dark Ages will begin. Hundreds of millions of years of a starless, silent, waiting universe. And then, the first light, the first stars, the dawn of the universe. Lie back comfortably, take a deep breath, and let me carry you through that long night and into the coming dawn. 380,000 years, the Great Illumination. The universe is 380,000 years old. The temperature has dropped to 3,000 Kelvin, still extremely hot, about half the surface temperature of the sun, but below a critical threshold. And at that moment, something happens. Electrons are now slow enough to bind to protons. Electromagnetic attraction overcomes kinetic energy. Recombination begins. An electron and a proton, the first hydrogen atom, is formed. One electron, one proton, the simplest atom, and at the same time, the most important one. Because once hydrogen atoms form, free electrons disappear, and without free electrons, photons are no longer scattered. Light is free. For the first time, photons can travel in straight lines without colliding with anything, across infinite distances. The universe becomes transparent. It is as if a dense fog suddenly lifts, and for the first time, you can see far, infinitely far. Yet there is a paradox. At that moment, there is no one to see it. No eyes, no life, only atoms, hydrogen, and helium. Still, the light begins its journey, and that light travels through space for 13.8 billion years. And today, that light reaches us, the cosmic microwave background. The cosmic microwave background, the universe's first photograph. The light released at 380,000 years is still there, but it is no longer visible light, because the universe has expanded, and expansion stretches light waves, redshifting them.
So much so that the light is no longer even infrared. It has become microwaves. We call this light the cosmic microwave background. In 1965, Arno Penzias and Robert Wilson discovered it by accident. They were calibrating an antenna, but strange noise was coming from every direction. At first, they thought it was bird droppings. Pigeons had nested inside the antenna. They cleaned it. The noise remained. Then they realized this was the sound of the universe, the echo of the Big Bang. That discovery won the Nobel Prize because it was the strongest evidence for the Big Bang theory. Today, satellites like Kobe, WOMAD, and Planck have mapped the CMB in extraordinary detail. And those maps show us what the universe looked like at 380,000 years old. Almost perfectly uniform, but with tiny fluctuations. Temperature differences at the level of 1 part in 100,000. Those tiny fluctuations are the seeds of the future, because in those regions, matter is slightly denser, gravity is slightly stronger. And millions of years later, the first stars will be born there. The CMB is the universe's birth certificate, its baby picture. And that picture is still hanging on the wall in every direction of the sky. If you have an old television and it is not tuned to any channel, about 1% of the static noise on the screen comes from the CMB. Yes, the interference on your television is partly the echo of the Big Bang. The universe's first light is dancing on your screen.
The Dark Ages begin. A starless night. Light has been set free. The universe is transparent. But strangely, the universe grows darker. Why? Because those bright photons are spreading out into space, dispersing, and there are no new sources of light. There are no stars yet, because stars require gravity to form, and gravity takes time. Matter must slowly come together. For the first few 100 million years, the universe is dark. The Dark Ages. Not completely dark, though. Hydrogen atoms emit a faint signal, a wavelength of 21 centimeters, a radio frequency, invisible to the eye, but real. If you were there at that time, which is impossible, the sky would be completely dark. No stars, no galaxies, no moon, no sun, only endless, deep, silent darkness. But that darkness is not truly silent, because something is happening, invisible but real. Matter is slowly gathering. Gravity is at work. Tiny differences in density are growing. Dark matter, which we still do not truly understand, pulls matter together, forming filaments, a cosmic web. And at the nodes of that web, clouds of hydrogen grow denser. They collapse. They heat up. One day, they will become dense enough. Their centers will become hot enough, and fusion will begin. The first star will be born. But that will take 100 to 200 million years. For now, we wait in the dark. The first structures, the invisible hand of dark matter. During the Dark Ages, even though nothing visible exists, something is building structure. Dark matter. Dark matter outweighs normal matter by about 5 to 1, but it emits no light, absorbs no light. It is completely invisible. Yet it has mass, and mass creates gravity. Dark matter is the skeleton of the universe, an invisible framework. Normal matter, hydrogen and helium, gathers along that framework. The first structures are dark matter halos, huge spherical regions millions of light years across. Inside these halos, normal matter accumulates.
Hydrogen clouds collapse, falling toward the center. Gravity compresses them. Temperature rises. Pressure increases. But still no fusion, because it is not yet hot enough. 100 million years pass. Dark, silent, but filled with anticipation. And then, somewhere, a critical threshold is crossed. The core temperature reaches 10 million Kelvin. Protons collide. They fuse. Fusion begins. The first star ignites. The first stars, population 3, pure and massive. 200 million years have passed. Some estimates say 100 million, others 400 million. We do not know for sure. And somewhere in the deep darkness of the universe, a single point begins to shine. The first star. A population 3 star. Not the third generation, the first. The naming was done retroactively. And these stars are very different because they are made only of hydrogen and helium. No carbon, no oxygen, no iron. Those elements do not yet exist. They are created inside stars. But the first stars were not born from earlier stars, so they are pristine, pure. And that purity makes them enormous. Normal stars, like our Sun, use heavy elements to regulate energy efficiently. Population 3 stars lack that advantage. As a result, they must be huge, 100 to 200 times the mass of the Sun, perhaps even more. They are incredibly bright, millions of times brighter than the Sun, and extremely hot. Surface temperatures of 50,000 Kelvin or more. The Sun's surface is only about 5,800 Kelvin. They shine blue-white, intense, powerful. But they live short lives, only a few million years. They burn furiously, exhausting their fuel quickly. And then they explode. Gigantic supernovae, perhaps even hypernovae. In those explosions, heavy elements are forged. Carbon, oxygen, silicon, iron, all are scattered into space. Those elements will become the raw material for the next generation of stars. But for now, the first star shines, and the Dark Ages come to an end.
The dawn of the universe, reionization. The first star is born, then a second, then thousands more. Each one is incredibly bright, intensely energetic, and, most importantly, emits vast amounts of ultraviolet radiation. That ultraviolet light strikes the surrounding hydrogen atoms, knocking their electrons free. Hydrogen becomes ionized again. Protons and electrons separate. This process is called reionization, because right after the Big Bang, everything was already ionized. Then recombination happened, atoms formed, and now, once again, ionization returns. But this time it is different, because now there are stars, there are sources of light. Reionization spreads in waves, starting from the first stars and expanding outward. The universe becomes transparent again, but this time illuminated by starlight. The Dark Ages end. The dawn of the universe begins. This era unfolds roughly between 500 million and 1 billion years after the Big Bang. By the end of it, the entire universe is reionized. Darkness fades. Light prevails. The universe is now bright, filled with stars. Life begins. Well, not yet. Life will come much later. But the conditions are being prepared. Seeds of the first galaxies, small and chaotic. The first stars are not born in isolation. They form in groups, hundreds, thousands of stars together. Proto-galaxies,
Very small, only about a millionth the mass of the Milky Way, but highly active, extremely energetic, new stars forming constantly, supernovae exploding again and again. Chaos, but creative chaos. These proto-galaxies merge, they collide, they grow. Dark matter halos hold them together, and over time, larger structures emerge. But this process is slow. It takes millions of years. In the first 500 million years, only small proto-galaxies exist, irregular, shapeless. After 1 billion years, some have merged into larger galaxies. After 3 billion years, spiral galaxies, elliptical galaxies, and well-defined structures appear. The universe matures. Structures take shape. Order is born from chaos. The James Webb Space Telescope, seeing the dawn of the universe. In 2022, the James Webb Space Telescope began operations, and its first images were astonishing, because JWST observes infrared light, and infrared is perfect for seeing extremely distant galaxies. As the universe expands, light is stretched and redshifted. The light from the most distant galaxies shifts into the infrared. JWST can look 13 billion light-years away. It sees galaxies formed just 500 to 700 million years after the Big Bang. The dawn of the universe, the era of the first stars. And what we see is surprising. Those early galaxies are larger, brighter, and more organized than expected. It is as if the universe matured faster than our models predicted. We are still trying to understand this, but one thing is certain: the first stars and the first galaxies are far more fascinating than we imagined. And JWST is showing us that era for the first time. Childhood photographs of the universe from 13 billion years ago. And in those images, we see the seeds of the future, the ancestors of our Milky Way, the grandmother galaxy of our Sun. Everything began there. End of the second chapter, From Darkness to Light. Take a breath, deep, slow. In this chapter, you witnessed the longest night of the universe. At 380,000 years, light was released, but then the Dark Ages began. For 100 to 200 million years, the universe was starless and silent. Then the first star was born, population 3, massive, brilliant, short-lived. And those stars defeated the darkness. The universe shone again, reionization, dawn. The first galaxies began to form, small, chaotic, yet creative. In the next chapter, we will enter the age of galaxies, from 500 to 3 billion years after the Big Bang, an era of galactic mergers, the birth of supermassive black holes, and the creation of heavy elements. The universe's youth, its golden age. But for now, simply rest. Your eyes may close, your thoughts may drift, your body may sink into the bed. The Dark Ages are over, light has returned, and the universe has begun to live.
Cosmic cities. Welcome back. Or perhaps you never left. Maybe by now the words have turned into background music. Maybe your body has relaxed so completely that you can no longer tell where you end and where the bed begins. Perfect. Because in this chapter, we are entering the most dynamic, most creative era of the universe. In the first 2 chapters, we witnessed the beginning, the first 3 minutes, the Dark Ages, the first stars. But now, 500 million years have passed. The universe is no longer a baby. It is a child, energetic, growing, taking shape.
Galaxies are forming, merging, colliding. Giant black holes are being born. Heavy elements are being created. This is the golden age of the universe, its brightest period, its most creative moment. Lie back comfortably, take a deep breath, and let me carry you into the era when cosmic cities were being built. 500 million years, the first true galaxies. The first stars were born in isolated groups, hundreds, thousands of stars together, but they were not yet galaxies. But now, 500 million years later, something changes. Gravity is at work. Dark matter halos pull in normal matter. Star groups drift closer to one another. They collide, they merge, and larger structures emerge, the first true galaxies. But they are nothing like our Milky Way. Much smaller, perhaps only 1% of its mass, and highly irregular. No spiral arms, no orderly disk, just a chaotic collection of stars. Yet they are extremely active. Their rate of star formation is enormous, hundreds of times faster than in our galaxy. Why? Because there is gas everywhere. Vast clouds of hydrogen and helium fill space. Everywhere is a star factory. New stars are constantly being born. They shine, they explode, supernovae everywhere. Chaos, but a beautiful chaos, creative, overflowing with energy. These galaxies are called starburst galaxies because star formation is so intense that the galaxy seems to blaze, pouring all its energy into making stars. And this phase lasts millions of years until the gas runs out. Galaxy mergers, cosmic dances. But galaxies are not isolated. Nearby, there are other galaxies, and gravity pulls them together. Two galaxies begin to approach one another, slowly, over millions of years. At first, from afar, just a gentle tug. Then closer, gravity strengthens, galaxies distort, spiral arms stretch, stars are flung outward, and finally, collision. But it is a strange kind of collision, because galaxies are mostly empty space. Stars are incredibly far apart. The chance of two stars actually colliding is extremely small. But gas clouds do collide, and when they do, they compress. Temperature rises, pressure increases, and suddenly, massive star formation begins, a starburst. The galaxy gives birth to millions of new stars at once. Brilliant, energetic, short-lived. Because the gas is consumed rapidly, within a few 100 million years, it is gone. But during that time, the galaxies have merged. They have become a single larger galaxy. And this process happens again and again. Small galaxies merge to form larger ones. Then those merge as well. Galaxy evolution is hierarchical, from small to large, from chaos to order. Billions of years later, giant spiral galaxies and elliptical galaxies will emerge. But for now, there is only chaos, endless merging, endless creation. The birth of supermassive black holes, monsters at the heart. At the centers of galaxies, something strange is happening. Enormous amounts of matter are flowing inward. Gravity pulls it in, stars, gas, dust. Everything spirals toward the center. And the core becomes incredibly dense, incredibly hot, incredibly energetic. At some point, something collapses. Perhaps a cluster of stars, perhaps a direct cloud of gas, but a singularity forms, a black hole. But not a small one, a massive one. Thousands, tens of thousands of times the mass of the sun. A supermassive black hole. How did it grow so fast? We do not know. Because under normal conditions, black holes grow slowly. They must consume matter, and matter usually flows in gradually. But in the early universe, there was an abundance of matter. it flowed rapidly, and black holes grew extremely fast. Perhaps the first black holes were born from the collapse of population 3 stars. Those stars were enormous, 100 to 200 times the mass of the Sun. When they died, they left behind black holes, seed black holes. And those seeds grew quickly. They devoured surrounding matter. They merged with one another. They became larger and larger. Within 1 billion years, some black holes reached billions of solar masses, truly colossal. These black holes settled at the centers of galaxies, because the center is the densest region, where matter is most abundant. Today, almost every large galaxy has a supermassive black hole at its core. At the center of the Milky Way, Sagittarius A star, 4 million solar masses. At the center of Andromeda, 100 million solar masses. In the galaxy M87, 6.5 billion solar masses. These black holes are the hearts of galaxies, silent but immensely powerful. Quasars, the brightest beacons in the universe. But some black holes are not silent. If there is a large amount of matter around them, that matter flows toward the black hole, forming an accretion disk. And that disk becomes unimaginably hot. Friction, magnetic fields, enormous energy. The disk shines brilliantly, brighter than an entire galaxy, a quasar. Quasars are the brightest objects in the universe. A single quasar can outshine trillions of stars. How is this possible? Because black holes are extraordinarily efficient. As matter falls into a black hole, 10 to 40% of its mass is converted directly into energy. In stars, nuclear fusion is only about 0.7% efficient. That means black holes are roughly 50 times more efficient than stars. That is why quasars shine so intensely. And in the early universe, quasars were everywhere because there was vast amounts of gas. Black holes were constantly being fed. But over time, the gas was depleted. Quasars faded. Only quiet black holes remained. Today, the nearest quasar is billions of light years away because quasars are a feature of the early universe, its youth. Now the universe has aged. It has calmed. Quasars have become rare. But back then, the sky was filled with them. Bright, powerful, overflowing with energy. The golden age of the universe. The creation of heavy elements, supernova factories. The first stars burned only hydrogen and helium, but inside them heavier elements were forged: carbon, oxygen, silicon, iron. Yet those elements remained trapped within the stars. They were not released into space until the star died, a supernova. A massive star exhausts its fuel. Its core becomes iron, but iron fusion consumes energy. It does not produce it. There is no longer any support. The core collapses suddenly. The outer layers fall inward. They crash into the core. A shockwave forms, and everything is blasted outward. A supernova explosion. In that explosion, an unimaginable amount of energy is released, more in a single second than the sun will emit over billions of years. And that energy creates the heavy elements: iron, nickel, gold, platinum, uranium. All of them are forged during supernovae. Then those elements are scattered into space, mixing with vast clouds of gas. The next generation of stars is born from this enriched material, no longer just hydrogen and helium, but carbon, oxygen, iron as well. Around those stars, planets form, rocky planets, because carbon, silicon, and iron are now present. And on those planets, one day, life can arise, because carbon is the foundation of life. So supernovae are not only destruction, they are also creation. They produce the raw materials of life. The iron in your blood was forged in a supernova. The calcium in your bones was forged in a supernova. The carbon in your DNA was forged in a supernova. You are made of star ash, not just stardust, the ashes of dying stars. Supernova ash.
1 to 3 billion years. The maturation of galaxies.
Time continues to flow. 1 billion years, 2 billion, 3 billion. Galaxies are now larger, more organized, more structured, more stable. Endless mergers have built massive systems. Some take on spiral forms, orderly disks, sweeping spiral arms, central bulges. Others become elliptical, rounded, smooth, with stars moving in random directions, often the result of major collisions. Galaxies resembling the Milky Way are beginning to appear. But the Milky Way itself does not yet exist. Our galaxy is younger, about 13 billion years old, so it began forming roughly 800 million years after the Big Bang. Still, its ancestors are already there. Small proto-galaxies, scattered and irregular. Over time, they merge and assemble into what will become the Milky Way. If we could rewind time and observe our galaxy 10 billion years ago, it would look very different. Smaller, more chaotic, and bluer, glowing with young, massive stars. Yet it is already itself. Growing, evolving, maturing. Around newly formed stars, planetary systems begin to take shape. Disks of gas and dust swirl into existence. Particles collide, stick together, grow larger. Planets are born. The first planets are often extreme, scorching hot, orbiting close to their stars. But some form farther out, cooler, where liquid water may exist. Potential habitats. But life has not yet emerged, at least not as far as we know. Because life is complex. It requires time, billions of years. Still, the ingredients are now present. Elements, planets, energy. One day, somewhere, life will arise. But that is another story, for another time. The golden age of the universe, its brightest era. Between 2 and 3 billion years after the beginning lies the universe's most luminous period. Why? Because star formation reaches its peak. Across the cosmos, galaxies are giving birth to stars at extraordinary rates. Everywhere, new suns ignite, quasars blaze, supernovae erupt, galaxies collide and grow. Energy fills space, light floods the universe. If you could stand beneath the sky at that time, it would be far brighter than today. More stars, more galaxies, more light in every direction. The universe is young, vigorous, radiant. But slowly, things begin to change. Gas is consumed, star formation declines, quasars fade. The universe ages. It calms. Yet the golden age is never truly lost. The stars formed then still shine today. The heavy elements forged then still exist. We are the children of that era. The sun was made from those elements, the earth from them, and we are too. The golden age has passed, but its legacy endures. Take a breath, deep, slow. In this chapter, you have witnessed the age of galaxies, from 500 million to 3 billion years after the beginning. The most dynamic era of the universe. The first galaxies formed, merged, and grew. Supermassive black holes were born. Quasars blazed. Supernovae forged the elements. The universe moved from chaos to structure, from randomness to order. Cosmic cities were built. In the next chapter, we will turn toward our own story. 4.6 billion years ago, the birth of the solar system, the formation of Earth, the emergence of life, and eventually human civilization. Out of 13.8 billion years of cosmic history, only the last 4.6 billion concern us directly. But for us, they are everything. For now, rest. Your eyes may close, thoughts may drift, your body may grow heavy. Galaxies have turned, stars have been born, elements have been forged, and now everything is ready for life, for consciousness, for you.
Perhaps by now, your body has relaxed so deeply that it almost feels as if it no longer exists. Only consciousness remains. Only awareness, quietly listening. Perfect. Because in this chapter, the cosmic story becomes personal. In the first 3 chapters, we followed the grand narrative of the universe, from the Big Bang to galaxies, from stars to heavy elements. But now we travel to 4.6 billion years ago, to one spiral arm of the Milky Way, to an ordinary cloud of gas. And there, something happens. Small, yet profound. Local, yet with universal consequences. The solar system is born. And within that system, a small blue planet will form. And on that planet, a miracle will occur. Life. Settle in comfortably. Take a deep breath and allow me to guide you back to our own origins. Nine billion years have passed. The Milky Way has matured. The universe is now 9 billion years old. Much has changed since the Big Bang. The first stars have died, galaxies have merged, the Milky Way has taken shape. It is now a spiral galaxy, 100 billion stars, 100,000 light years across, beautiful, ordered, mature. At its center, the supermassive black hole is calm, no longer a quasar, just sitting there, silent. In the spiral arms, star formation continues, but slowly, the golden age has passed. Now creation is steady, patient, restrained. And in one of those arms, the Orion arm, there is a cloud of gas and dust, the solar nebula. Several light years wide, hydrogen, helium, and heavier elements, carbon, oxygen, iron, the inheritance of earlier generations of stars. That cloud has been there for millions of years, quiet, still, cold. And then something happens. A nearby star explodes as a supernova. Its shockwave slams into the cloud, compresses it, densifies it. Gravity takes over. The cloud begins to collapse toward its center, slowly but inevitably. The birth of the solar system has begun.
4.6 billion years ago, the ignition of the sun. As the cloud collapses, it begins to rotate. Angular momentum. Everything spins. The center grows denser. Temperature rises. Pressure increases. After a few 100,000 years, the core becomes extremely hot, millions of degrees. A critical threshold is crossed. Protons collide. They fuse. Nuclear fusion begins. The sun ignites. The first light, the first warmth, the first breath. The sun has become a star, medium-sized, a yellow dwarf, ordinary, yet for us, everything. But around it, a disk still remains, gas and dust, a flat, rotating disk, the protoplanetary disk. From this disk, planets will be born. The seeds of the first planets. Within the disk are tiny dust particles, micrometer-sized grains of carbon, silicon, iron. These particles collide. Sometimes they stick together. Electrostatic attraction. Slowly they grow, millimeters, centimeters, meters. Planetesimals form, small rocky bodies kilometers across. And those planetesimals collide with one another. They merge, they grow larger. Some become massive enough that gravity takes over, pulling in surrounding material. Protoplanets are born. And competition begins. The large consume the small. The strong grow stronger. After 100 million years, only a few large planets remain. The rest have been swallowed or ejected. The inner planets, rocky worlds. Close to the Sun, it is too hot. Light gases, hydrogen and helium, escape. The solar wind sweeps them away. Only heavy elements remain: rock, metal. 4 rocky planets form. Mercury, the smallest, the closest, scorched. No atmosphere, just bare rock. Venus, Earth's twin, but a hellscape. A dense CO2 atmosphere. Temperatures of 450 degrees Celsius. Clouds of sulfuric acid. Earth, the third planet. The perfect distance. The Goldilocks zone. Not too hot, not too cold, just right. Mars is the fourth. Small, red, cold. Once had water, now barren. The outer planets, gas giants. Far from the Sun, it is cold. Light gases can condense. Large planetary cores pull in these gases, forming massive atmospheres. 4 giant planets emerge. Jupiter, the king, the largest in the solar system. 300 Earth masses. Hydrogen and helium. Gigantic storms. The Great Red Spot. More than 80 moons. Saturn, the ringed beauty. Rings of ice and rock. Its moon Titan with methane lakes. Exotic and strange. Uranus, the tilted one. An axial tilt of 98 degrees. An ice giant. Methane blue. Cold. Mysterious. Neptune, the farthest. The windiest. Winds up to 2,000 kilometers per hour. Deep blue. Its moon Triton orbiting backward. And beyond them, the Kuiper Belt. Icy bodies. Pluto, other dwarf planets. The home of comets. 4.5 billion years ago, the giant impact and the birth of the moon. Earth has now formed, but it is very different. A molten ocean of lava, no atmosphere, just a hot, raging sphere. Then something happens. A Mars-sized protoplanet is approaching Earth. Its name is Theia. The collision is inevitable. 4.5 billion years ago, Theia strikes Earth. Not head-on, a glancing, angled impact. Enormous energy is released. Part of Earth is blasted into space. So is part of Theia. Molten rock, vapor, magma. That debris begins to orbit Earth, forming a disk. And within a few million years, the material comes together. The moon is born. This is the most widely accepted theory of the moon's origin, the giant impact hypothesis. And there is evidence. The moon's composition is remarkably similar to Earth's mantle because it came from the same material. At first, the moon was very close, only about 20,000 kilometers away. Today, it is 384,000 kilometers. It would have looked enormous in the sky, 15 times larger than today. And the tides were extreme. Not only the oceans, but even the land itself rose and fell. But slowly, the moon has been drifting away. Tidal friction, about 3.8 centimeters per year. Billions of years from now, it will be very far away, a small point in the sky. No eclipses. But for now, the moon is here. Not just beautiful, but essential. Because the moon stabilizes Earth, its axial tilt, its climate, its seasons. Without the moon, Earth's axis would wobble, the climate would be chaotic, life would be far more difficult. So the moon is not just a satellite, it is a guardian of life.
4.4 to 3.8 billion years ago, Earth calms down. After the impact, Earth slowly begins to cool. The surface solidifies, the first crust forms, but it is still intensely volcanic. Everywhere lava flows and gases erupt. An atmosphere forms, but there is no oxygen. Mostly carbon dioxide, nitrogen, water vapor, methane. Toxic. Water vapor condenses, clouds form, and rain begins. But not ordinary rain, floods. Rain that lasts for millions of years. Water accumulates on the surface, in depressions, in valleys. The first oceans form. But the bombardment is not over. The late heavy bombardment from 4.1 to 3.8 billion years ago, huge asteroids and comets repeatedly strike Earth. Some are large enough to vaporize entire oceans. Then, around 3.8 billion years ago, the bombardment declines. The solar system is cleaned up. The major debris is gone. Earth finally becomes calm, stable, liquid water, a steady atmosphere, ready for life. 3.8 billion years ago, the first spark of life. And somewhere in the depths of an ocean, something happens. Chemicals come together. Amino acids, nucleotides, organic molecules. Perhaps near hydrothermal vents, hot, mineral-rich water, a source of energy. Perhaps in shallow pools, sunlight, lightning, energy. We do not know. But somehow, the first self-replicating molecule forms, RNA, or something like RNA. And that molecule copies itself, with errors, with mutations. Some copies are better, faster, more stable. Natural selection begins. Evolution has started. The first LUCA forms, the last universal common ancestor. The ancestor of all life, yours, mine, trees, bacteria, everything. Very simple, single-celled, but alive. It has metabolism, it reproduces, it grows. Life has begun, and it will never stop again. 3.5 billion years ago, photosynthesis and the oxygen revolution. The first life forms are simple, bacteria, single-celled, living in the depths of the ocean. But around 3.5 billion years ago, something changes. Some bacteria acquire a new ability, photosynthesis. They use sunlight, they take in water and CO2, they produce sugars, and as a byproduct, they release oxygen. Cyanobacteria, blue-green algae. At first, the oxygen dissolves in the oceans. It reacts with iron, forms rust. That is why there are red iron oxide layers on the ocean floor. But around 2.4 billion years ago, the oceans become saturated. Oxygen begins to spread into the atmosphere. The Great Oxygenation Event. Atmospheric oxygen rises from 0% to about 21%, today's level. But this is a massacre. For most life at the time, oxygen is poisonous. Most organisms die. But some adapt. They develop oxygen-based respiration, far more efficient, far more energetic.
and those organisms become dominant. The oxygen revolution transforms life. It makes complex life possible.
600 million years ago, now, explosive evolution. For billions of years, life remained simple. Bacteria, algae, single-celled organisms. But around 600 million years ago, something explodes. The Cambrian explosion. Multicellular life suddenly diversifies. Every shape, every size. Trilobites, jellyfish, the first vertebrates, the first eyes. Evolution accelerates. Around 500 million years ago, plants move onto land, the first green landscapes. Around 400 million years ago, animals follow. The first amphibians crawl ashore. Around 300 million years ago, dinosaurs become dominant. Then, 65 million years ago, an asteroid strikes. The dinosaurs disappear, but mammals survive, and evolution continues. Around 7 million years ago, the first hominins appear, creatures that walk upright. Around 300,000 years ago, Homo sapiens emerges, modern humans, us. The last 10,000 years, civilization. For about 300,000 years, humans lived as hunter-gatherers. Then, around 10,000 years ago, agriculture begins. The first cities, the first writing, the first civilizations. In the last 200 years, the Industrial Revolution, an explosion of technology. In the last 100 years, airplanes, computers, space travel. In the last 50 years, the internet, artificial intelligence, and genetic engineering. Humanity is advancing rapidly. And now, here we are, at the end of a 13.8 billion year cosmic story. Or perhaps at the beginning. Who knows? End of the 4th chapter, our moment. Take a breath. Deep. In this chapter, we followed our own story, from the birth of the sun 4.6 billion years ago to today. Planets formed, Earth calmed, life began. Evolution carried us from simple cells to humans. And now we are here, a part of the universe that can understand itself. In the next chapter, we will look to the future. 5 billion years from now, the death of the sun, the collision of the Milky Way and Andromeda, the birth of the last stars, the slow darkening of the universe. But for now, simply stay with this moment. Because you are lucky. You are the result of a 13.8 billion year cosmic journey, the product of trillions of coincidences. And now you are conscious. You know that you exist. 1 billion years later, Earth's difficult era. Now we move 1 billion years into the future. The sun has aged, brighter, hotter. Nuclear fusion is slowly accelerating. The heat reaching Earth increases. The oceans begin to evaporate. Water vapor rises into the atmosphere. The greenhouse effect strengthens. More heat is trapped. A runaway greenhouse effect begins. The oceans slowly disappear. Clouds diminish. Rainfall stops. The continents turn into deserts. Plant life dies. Photosynthesis ceases. Oxygen in the atmosphere decreases because no new oxygen is being produced. Complex life goes extinct. Animals, plants, all gone. Only some extreme bacteria survive, underground, deep within rocks, but even they will eventually disappear. Earth slowly turns into Venus, scorched, barren, lifeless. If humanity still exists, it has long since migrated to Mars, to Jupiter's moons, maybe to other star systems, or perhaps it is extinct as well. Who knows? But life on Earth is now approaching its end. 4 billion years later, the Milky Way and Andromeda, a cosmic dance. Now we jump 4 billion years into the future. We pull back from the solar system and look on a galactic scale. The Milky Way and Andromeda have been approaching each other for billions of years. Gravity has been drawing them together. And now the collision finally begins. But collision is the wrong word, because galaxies are mostly empty space. Stars do not crash into each other. The distances are far too vast. But the shapes of the galaxies change. Gravity tugs at the stars. Spirals distort. Chaos. The two galaxies pass through each other, interpenetrate, drift apart, then approach again. A dance that lasts billions of years. Some stars are flung outward into intergalactic space, alone forever. Some stars are pulled inward toward the supermassive black holes at the centers. And those two black holes, the one at the center of the Milky Way and the one at the center of Andromeda, merge. A gigantic black hole is born. In the end, when the chaos settles, a new galaxy remains, Milkomeda or Milkdromeda, an elliptical galaxy, larger but less orderly, no spiral arms, just a massive sphere of stars. And the Sun? It is still there, maybe in a different orbit, maybe flung to the outskirts of the galaxy, but it is still shining. It has not died yet. 5 billion years later, the death of the Sun. Now we return to the solar system. 5 billion years have passed. The Sun is 10 billion years old. The hydrogen in its core is exhausted. Fusion slows down. It is about to stop. Gravity compresses the core. Temperature rises, but there is not enough hydrogen left. The outer layers begin to expand. The Sun swells. The red giant phase. The Sun becomes enormous, hundreds of times larger. It engulfs Mercury. It engulfs Venus. And Earth? Perhaps it is swallowed. Perhaps it survives, only to be scorched. Its surface completely molten, an ocean of lava. Nothing remains. But in the Sun's core, something new begins. Helium fusion. Helium atoms merge. Carbon and oxygen are formed. The Sun ignites again, a temporary rebirth. But it is short-lived, a few 100 million years. Then the helium too is exhausted. And the Sun is not massive enough to fuse heavier elements. It cannot go supernova. Instead, it sheds its outer layers, casting them into space. A planetary nebula forms, a beautiful, colorful cloud, expanding gas and dust. And what remains is only the core, a hot, dense remnant, a white dwarf. Earth-sized, but with the mass of the Sun, incredibly dense. There is no fusion anymore, only heat, slowly cooling, bright white, then yellow, then red, then darkness. After billions of years, it will become a black dwarf, completely cooled, invisible, but still there. The Sun has died, but it has not vanished. It has simply grown silent. 20 billion years later, the universe continues to expand. Now we look at the universe as a whole. 20 billion years have passed since the Big Bang. The universe is still expanding and accelerating. Dark energy is pushing everything apart. Galaxies drift away from each other. Galaxy clusters disperse. The universe becomes increasingly sparse, increasingly empty. But there are still stars, still galaxies, still life, if it exists elsewhere. Star formation has slowed because gas and dust are running out, but it has not completely stopped. Small red dwarf stars are still being born, slowly burning incredibly long-lived stars. The universe is old, but it is not dead yet. 100 trillion years later, the birth of the last stars. The universe has completely changed. New star formation has nearly stopped.
gas and dust are exhausted. Only existing stars still shine, and even they are fading one by one. Massive stars died long ago. They exploded as supernovae, leaving behind neutron stars or black holes. Medium-sized stars, like the Sun, became white dwarfs, cooling. But red dwarfs are still burning because they consume their fuel very slowly, lifespans measured in trillions of years. And the final red dwarf forms 100 trillion years after the beginning, the last new star in the universe. It too will burn for trillions of years, but eventually it will fade. After that, no new stars will ever be born. There is no fuel left. The age of star formation has ended. 1 quadrillion years later, the degenerate era. Only remnants remain. 1,000 trillion years equals 1 quadrillion years. The universe is completely dark. All stars are dead. White dwarfs have become black dwarfs, fully cooled, no light. Only remnants remain. Brown dwarfs, failed stars, they never ignited, cold balls of gas. Black dwarfs, former white dwarfs, completely cooled, invisible. Neutron stars, leftovers of ancient supernovae, still there, but silent. Black holes, large, medium, small, of every kind, in galactic centers, in binary systems. Planets, lonely and dark, torn from their stars, drifting through space. The universe is a graveyard. Not even a graveyard, really, because it is silent, cold, motionless. The degenerate era. But gravity still exists, and gravity, even if extremely slowly, still works. Galaxies gradually evaporate. Stellar remnants fling one another away through close encounters. After 100 quadrillion years, most remnants in a galaxy are ejected into intergalactic space. What remains is only the central supermassive black hole and a few nearby remnants. They too slowly fall in. Galaxies become nothing but black holes. 10 to the 40th years. Now the numbers become absurd. 10 to the 40th years. 10 million years. The universe is almost completely empty. Only black holes remain, large, medium, small, floating through space. But black holes are not eternal. Hawking radiation, Stephen Hawking's discovery. Black holes evaporate incredibly slowly. Small black holes evaporate faster, large ones more slowly. A black hole with the mass of the Sun evaporates in about 10 to the 67th years. Supermassive black holes with billions of solar masses evaporate in about 10 to the 100th years, a Google years. Unimaginably long, but finite. And one day, the last black hole evaporates. The final light flickers. The last energy is released. And then, nothing.
10 to the 100th power years later. The Dark Age. Only photons remain. The universe is now completely empty. No matter, no stars, no planets, no black holes. Only photons remain. Particles of light, but extremely diluted, with enormously long wavelengths. Not even radio waves, longer than that. The universe is in thermal equilibrium, the same temperature everywhere, close to absolute zero. Entropy is at its maximum. Disorder is complete. Heat death. Nothing can happen because there are no energy differences, no gradients. The universe is silent, cold, dark, motionless, forever. Or maybe not, because some theories suggest that quantum fluctuations can create new universes. Perhaps if you wait long enough, an incomprehensible span like 10 to the 156th power years, quantum chance could trigger a new Big Bang. The Boltzmann brain hypothesis. random fluctuations giving rise to momentary consciousness or even an entire universe. But these ideas are speculative. We do not know. What we do know is this: this universe is slowly fading away. End of the 5th chapter. The sadness and beauty of the end. Take a deep breath. This was a heavy chapter. Trillions, quadrillions, Google years. The slow death of the universe. The sun died, stars went out, black holes evaporated. Only cold, darkness, and emptiness remained. Depressing? Maybe. But it also gives perspective. Because now you understand how precious the universe is. Right now, this moment. Stars are shining, planets are turning, life exists. And you are here. You are conscious. You feel. You think. That is a miracle. A temporary miracle. But that is exactly why it is so valuable. Because one day, in the unimaginably distant future, there will be nothing. But now, there is everything. And that is enough. In the 6th and final chapter, we will ask the deepest questions. What is the meaning of life? What is our role in this cosmic story? How do we find meaning in a finite universe? But for now, just lie back, breathe, and feel the miracle of being here. Cosmic perspective. You are the miracle of the universe. Let us begin with a fact. You did not arrive here by chance. You are the result of a 13.8 billion year process. The first quantum fluctuations at the Big Bang, the formation of hydrogen atoms, the birth of the first stars, the explosions of supernovae. In those explosions, heavy elements were created: carbon, oxygen, iron, calcium. Those elements formed a new star system, the solar system, and within that system, a planet formed, Earth. And on that planet, a miracle occurred: life. Billions of years of evolution, from single cells to multicellular life, from sea to land, from dinosaurs to mammals. And 300,000 years ago, a conscious species emerged, Homo sapiens. And from that species, you were born. Every atom in your body was born inside a star. Your carbon came from an ancient red giant, your oxygen from the core of a massive star, your iron from a supernova, your calcium from a neutron star collision. As Carl Sagan said, we are made of star stuff. But not only physically, consciously as well. Because for billions of years, the universe was unconscious. Only atoms, gases, stars. No one thinking, no one feeling. And then you appeared. And now the universe knows itself. You are the universe looking back at itself. Again, Carl Sagan, we are a way for the cosmos to know itself. This is a powerful and comforting idea, because it means you are not insignificant, quite the opposite. You are one of the most complex, rare, and magnificent products of the universe, the result of trillions of coincidences, a perfect convergence of conditions. And now you are here. You are conscious. You know that you exist. This is a miracle. Impermanence and value. Because it is finite, it is precious. But there is also a difficult truth. We are all temporary. You will live 80 to 100 years, maybe less, maybe a little more. Then you will be gone. Your consciousness will shut down. Your memories will fade. And not just you, everyone, everything. Earth will be gone in 5 billion years when the sun becomes a red giant. The Milky Way will collide with Andromeda in about 4 billion years.
The last stars will go dark after 100 trillion years. Black holes will evaporate after a Google years. The universe will eventually become completely cold and dark. Everything will end. Is that terrifying? Depressing? Maybe, at first. But consider this. If everything lasted forever, would it be valuable? If nothing were ever lost, would we care? Impermanence creates value. A sunset is beautiful because it is temporary. It will be gone in minutes, so we watch it closely. A song is meaningful because it ends. You can play it again, but that moment is unique. Time with someone you love is precious because it is finite. One day they will be gone, or you will. That is why we live in the present, with attention, with gratitude. If you had infinite time, nothing would matter. But your time is limited, and that is why every moment matters. This is a core teaching of Buddhism, anicca, impermanence. Everything changes. Everything comes and goes. Suffering comes from resisting this, wanting things to be permanent. But when you accept impermanence, truly accept it, you become free. Because you are no longer afraid, you are simply living. You experience each moment as it is, fully, deeply. A finite life is not meaningless. On the contrary, it is meaningful because it is finite.
The great nothingness and existential freedom. But one question still remains. If the universe will eventually fade into nothingness, why do we bother at all? This is the question of existentialism. Albert Camus, Jean-Paul Sartre, Simone de Beauvoir, they say this: the universe itself does not give you meaning. There is no God, no cosmic plan. There is only you and an indifferent universe. This can be terrifying, an existential crisis, but at the same time, it is liberating. Because it means this: you create your own meaning. The universe did not assign you a role, and that means you are free. You decide what matters. You decide how to live. There is no destiny, only your choices. Viktor Frankl, the psychologist who survived Auschwitz, said this: everything can be taken from a person, but one thing, the last of the human freedoms, to choose one's attitude in any given set of circumstances. Even in the most horrific conditions, he showed that humans can find meaning, because meaning is not outside, it is inside. What do you value? What do you love? What do you live for? The answer is yours. How should we live? 3 principles. So what is the conclusion? What do we learn from this cosmic story? I propose 3 principles. 1. Live in the now. The past is gone. The future does not yet exist. There is only now. It sounds cliché, but truly think about it. How many times have you been stuck in the past? Regrets, mistakes, if only. How many times have you worried about the future? Fears, what if? But right now, what are you doing? Where are you right now? You are here, now, this breath. And this is the only reality. This is mindfulness, awareness, fully experiencing the present moment. When you eat, just eat. When you walk, just walk. When you talk to someone, truly listen. Put the phone down, quiet the thoughts, simply be. Now is the only thing you truly have. 2. Value what you love. Life is short, and no one on their deathbed has ever said, "I wish I had worked more. I wish I had made more money. I wish I had worried more." People say, "I wish I had loved more. I wish I had laughed more. I wish I had been braver. I wish I had been myself." What do you love? Family, friends, art, music, nature, science,
Writing? Creating? Whatever it is, give it time. Make it a priority. Because in the end, what is remembered are those moments. Moments of love, moments of connection, moments of meaning. Treat what is precious as precious, because it is temporary.
Finally, one last question. What do you want to leave behind? One day you will be gone, but your impact can remain. Maybe in your children, maybe in your students, maybe in the work you created, maybe in a piece of art, maybe in an idea, or maybe simply in a kindness you showed someone, a moment when you truly listened, a joke that made someone laugh. Small contributions matter. You do not have to save the whole world. You only need to touch one person, and that person touches another, and it continues. The ripple effect. The universe is vast. You are small, but small actions can create great effects. A smile, a thank you, a hug. Use your life in service of others, even if it is small. And here is one final thought. Maybe the universe has no consciousness. Maybe no one is watching. But maybe you are watching, and that is enough. Because you are not separate from the universe. You are a part of it. Your atoms come from stardust. Your consciousness is one of the ways the universe knows itself. You are universal, a fragment, but a real one. And if you live a beautiful life, with love, with meaning, with gratitude, then the universe is beautiful too, because you are the universe. Every time you do something kind, the universe is kind to itself. Every time you love, the universe loves. Every time you laugh, the universe laughs. This is a deep truth. You and the universe are not separate. You are parts of a single whole. As Alan Watts said, you are not a stranger in the universe, watching it from the outside. You are the universe, experiencing itself. So do not take yourself too seriously. Play the game. Laugh, love, live. Because you are a cosmic miracle. From the Big Bang to the Dark Age, from stars to you, this is the story of the universe. And at the same time, it is your story. Now, one last time, take a deep breath, in and out. Feel your body, its weight, its warmth, its breath. Feel your awareness, your thoughts, your presence. And remember, you are a 13.8 billion-year-old miracle. You are made of stardust. You are one of the ways the universe knows itself. You exist here and now, and that is enough. I hope this journey has given you something, perhaps a wider perspective, perhaps deeper gratitude, perhaps a calmer heart. Whatever it is, thank you for listening, for being here. Now you may open your eyes or keep them closed. You may sleep or you may wake. Wherever you are, whatever you are doing, be gentle, be loving, live the miracle of being. Good night, farewell, and remember, you belong to the universe, and the universe belongs to you.